Alright, welcome back to the loop slides. Let's finish them up and start some new ones. So what I'd like to get into in these last two slides is using nested loops to do extra cool stuff. And this will help us get ready for our next lab. So I would like to graph a circle for you on the terminal. Crazy enough. So here's of course the equation for a circle, but it's really essentially about drawing a box, because that's going to be the window that we look into and we graph on. Okay, so let's draw a 78 by 24 box of stars right now. Okay, let's do that, because most terminal windows are at least that big and wide, so that'll be a good starting point for us. Okay, so we have a height 24, a width is 78, and I'd like to draw just a box of that many stars right now. And if you remember from last time, the outer loop worries about which row we're on, so I need an outer loop that iterates 24 times, and then the inner loop worries about drawing the 78 stars on the line, so that inner loop needs to loop 78 times. Okay, so let's set that up. So for int I equals 0, I is less than 24, because that's how many lines we want. And then on the inside, we want to go for j, right? So j is going to start at 0, but it's going to go to 78, right? Or 77. And that will get us as many stars as we need, right? And then a new line after that many stars, and that should do it. The reason I'm not making a second terminal right now is because I need the whole window to show you this. So let's compile and run that. Whee! There it goes. What have I done wrong? I plus, sorry, j is less than 78. That'll do it. There. Alright, so that's my window in which I'm going to graph things. So instead of a bunch of stars, I'm going to draw a bunch of spaces mostly, and then like, here's the 0, 0 coordinate. Right there, that's 0, 0. And then I want to draw like a circle made of stars around that circle, or around that 0, 0. So here's my best drawing of a circle made of star characters. Okay, that's what we would like to do. And so we noticed that I is just like y, right? And j is just like x, because I worries about which line we're on, right? And that's y coordinates. And j is which column we're on. Those are x coordinates. So let's change that real quick. So this is y, plus plus, and x plus plus. That's better. It'll still do the same thing right now. Also, what I'd like to do is have x and y be 0 in the very middle of this screen, because that'll be useful. Let's make that happen, okay? What do we need in order for that to happen? Well, we better have the I values or the y values not range from, because right now they're ranging from what, y equals 0 up here to y equals 24 down here. That's the wrong direction anyway, but it has nothing to do with the coordinate system right now. We can fix that, okay? We can have the y values range from -11 to 12. That's 24 things, but 0 will be in the middle. Isn't that nice? Whee. So y equals 12 up here, let's say. And y equals -11 down here. You see how that will make y equals 0 be in the middle? That's perfect. And then let's do the same for x. Like, let's make x be -38 over here and range up until x equals 39, because that'll also put the 0x coordinate in the middle of our box. Okay? And with that, I can check where I am, and I can print, like, when I'm at 0, 0, I can print a plus sign, and it'll be right in the center. Won't that be great? So, yeah, we're just assuming that our graph, we're making a graphing calculator, and its window is 78 by 24, and we want the middle to be in the middle of that 78 by 24 box, so we'll just let the x and y values range in this way. Okay? That's what we would like. And that will let us do what we need to do. Okay? So instead of this, y starts at 0. Well, the first line is up here, so y better start at 12 and go to negative 11. So greater than or equal to negative 11, and we're going downwards. And then x starts at, we said, negative 38, and it goes until positive 39, increasing. And so here is the exact same thing again, still a box being printed. Okay, recompile, rerun, same box. But now in the very middle is 0, 0, x equals 0, y equals 0. Let's make that happen. Let me prove that to you by printing a plus when x and y are both 0 instead of a star. Okay, it'll be hard to notice, but it'll be there. So if x is 0 and y is 0, then print a plus sign. That's like the axes meeting, right? Otherwise, print a star every other place on the graph. Okay, so that's my code. Again, I need the whole window to show you it running. Sorry, I gotta take it away for a second. But look right there in the middle. We have a plus sign instead of a star. So it's working. It's being centered properly. And with that, we can graph. Okay? So here is the equation of a circle, right? You know that a point is on the circle graph when the x squared coordinate plus the x coordinate squared plus the y coordinate squared is equal to the radius of the circle that you want to graph squared. That's the equation of a circle. And if this equation holds, then you are on the graph. Okay? That's what we want to be checking. We can have an if statement. So let's do that. All right, let's graph a radius 10 circle. So we'll pick the equation x squared plus y squared equals 10 squared. And we need to go and we need to figure out when this works. We need to figure out when this equation holds. Okay? So in the end, we want to graph something like this. We have our plus sign, and we have a bunch of stars that, once graphed, will be a radius 10 circle to us. Okay? So here's how you determine whether or not your current x and y coordinates are on this special graph that we care about plotting. We'll just do this. We will, for every x and y coordinate that we're ranging through, because we're doing that right now, we're ranging through every possible coordinate, right? We'll just check, see if it's on the graph. If so, draw a star. Okay? Otherwise, we'll draw a space. So normally, let's just draw a space instead of a star. The star is only if it's on the graph now. Okay? So now this is what I have. Now I want to draw my circle. Okay. So, what do I need to do? Check the current xy coordinate and see if it matches the equation. See if x squared plus y squared is really equal to 10 squared, right? I want to do something like that. I want to check, hey, is x squared plus y squared equal to 10 squared? And this would work if we had infinite precision, but it doesn't quite work. So here's how we're going to massage this equation to make it work in C++. Okay, we're going to first translate it into both halves, right? If you use a graphing calculator, you kind of have to plot it like this, right? You have to like solve for y, right? Y equals plus or minus, and then you take the square root because it's y squared. The square root of 10 squared minus x squared. And it's what, this is the equation that we're going to graph, okay? We'll graph both sides of it. We're going to graph the positive square root side and the negative square root side, okay? So that's the equation we're going to graph. For real, they're two separate equations, really, right? And then we're going to go through every possible xy coordinate as we see if we want to print a space, a star, or a plus, and potentially plot it if we're on the graph. So here's the trick. Our current xy coordinate needs to be plotted, needs to be a star. We know that it's on the graph if this is true, okay? Let's assume we're doing the top half right now, the positive square root. If y is equal to the square root, right, C math, of 10 squared, so that's 100, minus x squared, so x times x in C++, right? Or you could use pow, I guess. But notice that this is hardly ever going to be an integer, and y only ever gets to be integers, right? Same with x. So we can kind of shift it to the nearest one with a round, and that's what we'll do, okay? Because otherwise it would never be a perfect integer. We would never find a spot on the graph. We're just going to find the closest one by rounding. Okay? So round. Yay. That's how it works. Okay? That's also why we had to translate it to this, so that we could use round. Okay? So we're kind of squishing the decimals into the closest whole integer. I hope that makes enough sense. It'll be cool when we graph it, though. Okay? So what we need to do is we need to squish. I promise I can write the word need. Need to squish the decimals onto integer coordinates. Because this is square root hardly ever gives back an integer, right? Onto integer coordinates. Because that's all we have to work with when we're plotting. Okay, so with that, this will be the top half of the circle. So let's plot that. Okay, let's add an if statement that checks if this is ever true, and draw a star if it is. Okay, let's make it happen. So we'll do that first. If y is equal to, and I need CMath for round, among other things, square root, right? Round square root, this is the top half, 100 minus x squared, x times x. If this is true, then it's on the graph. Plot a star. Okay? That's a star character. Otherwise, let's bring these all together. It could be one big if else if else. Otherwise, maybe we are at the origin. Plot a plus sign just to show the axes meeting. And then otherwise, we're nowhere. We're empty space. We're not on the graph, nor are we right in the middle. So we're just going to draw a space character instead there. Okay? Just keep on going to the next coordinate, please. Okay? And with this, drum roll please, we should have a graph. Yay, there's the top half of my circle. Isn't that amazing? Isn't that cool how it's working like that? So that is the top half. If we want the bottom half of the circle, we'll just do the negative square root, okay? So we'll add that too. So on the top graph, and then if we're on the negative square root as well, we'll add a case for that. So let's do else if, and then another else if. Okay, so y is equal to negative round the square root, or round the negative square root, whatever you want to do. Either way will work. Okay, and this is on the bottom half of the graph. Hey, then we'll also plot a star. And with both of these halves, we will have our final answer. Boop. Boop. And look at my beautiful circle being plotted. Isn't that lovely? And so that's what you end up with. And let's go back to the code, okay? It's checking. It's going through every possible xy coordinate, checking to see if that pair of coordinates, that x and y, is related in the way that it should be related to be on the graph of a radius 10 circle. If that's true, squish to the nearest whole number, plot it. Same for the other side. Otherwise, maybe we're at the middle. We should take stock of that and show the user that we know where the origin is. Otherwise, we're just empty space. Okay? Just move on, get ready to maybe, like there was a space here, we gotta move over so that we can plot the star when it's our turn to plot that star. Okay? So there is my radius 10 circle being graphed. I hope that was fun. So that's going to be essentially the topic of your next lab. You're going to be making a graphing calculator like this. Okay, so definitely take use or make use of all this code that I just wrote here. All right, so that is my fun graphing calculator story for us. And now let's move on to a new set of slides. Okay, we have finished the loop slides now. Yay. So let's move on to the arrays and vectors slides. Are we ready? So you're actually kind of already familiar with this as far as arrays and vectors go, because you've learned about strings. You're going to see some things that are very similar to what I've already taught you about strings. Okay? So let's talk about arrays versus vectors, because these two words, they mean very similar things. Okay? Vectors are like cooler arrays. Okay? And so yeah, let me motivate all this, or at least introduce these topics. So arrays and vectors, these slides will teach us how to hold a bunch of stuff at once, right? Because right now, we're just holding single things at a time, like we're making a single variable. Arrays and vectors allow us to hold a bunch of stuff contiguously, looking like that. That's cool. So that's what we're going to learn about, how to make things that look like that you can put any data you want inside of here, okay? Multiple things. And I just want to highlight right now and emphasize that unless you're doing really, really low-level stuff, like you're an embedded programmer, and you really need speed, or you're doing multi-dimensional stuff, like you're working with not a straight line of information, but a grid of information, it is almost always a better idea to use a vector instead of a normal array. Okay? I'll talk about why later, but I just want to get you thinking that use a vector if you ever can. Okay? There are some times when you can't really do it, or it's harder to use a vector, but when you can, it will make your life so much easier. Okay? So with that, let's talk about arrays, because those are the easier of the two, the more simpler version. Vectors are built on top of arrays secretly. Okay, you'll learn about that in CSCI 41. So here we go. We want to hold a bunch of stuff of the same type. Okay, here's my motivation. Let's pretend that this is our problem. Somebody asks us to do this. We want to ask the user for 50 numbers. Please type 50 numbers to me, kind of like how you're doing in the tic-tac-toe lab. Ask the user for 50 numbers, and then print them out in order, in the order that you gave them, or do something cool with them. Maybe it's like a 50 by, like a 50 spots tic-tac-toe board or something. Who knows, but you need 50 things, and you need to save them. So what you know to do right now is make 50 separate variables, right? And cn each of them. And that is disgusting. Yes? We don't want that. That is a lot of typing. That just is a long program that does barely anything at all. Easy to make that go wrong. Okay, we don't like that at all. So let's fix it. Let us introduce a new kind of type, a type that holds other types. It's called an array. All right? So an array is your one-stop shop if you want to hold a bunch of stuff. It is a variable. You can make an array. It has a name, just like any other variable. But what it does is it holds a list of things, a list of data items, we say, each of the same type. So you can hold a bunch of ints, a bunch of chars, a bunch of doubles. They all have to be the same type. That's C++ for you. And then each of those individual things that you put inside of an array, it is a packaged deal, but you can go in and get each individual element. They're all directly accessible. Okay? So each little item inside of an array is called an element, and you can get at each individual element by indexing into an array, we say, using an operator that looks like this. It's the square brackets. Okay? So here is a line of code that declares an array of size 7 holding integers. Okay, this is how you read it. It's like R is an array size 7 of ints. The information is kind of strewn about the declaration. Okay, so you read this as R is an array of 7 ints. Okay, holds exactly 7 of them. So in memory, this is what it looks like. R exists, and it has 7 indices. 1, 2, 3, 4, 5, 6, 7. And the indices, are just like for strings, starting at 0, 4, 5, 6. You can access it like this. And because we declared it but never initialized it, what it's holding is complete garbage in each of these indices. Okay? So that's what R looks like. Let's talk about how to fill it with good stuff now. Okay? Declaring and initializing an array. Okay? So when you want to make an array, it's always element type, like int, the name of the array, just like any variable name, so R, whatever you need to put there. That's where your array name goes. And then in brackets, you can put the size of the array. If you're just going to declare it, you need to tell C++ how big it should be. Okay? Boop. There we go. So it's filled with garbage, just like every other variable. But if you want to access an index, you can go into it. Like, I want to access index I. Maybe I is 0, or you can hard code the 0 as well. I want to set this index of my array to 42, please. Okay? So, for example, here is me making an array of 3 ints. So it looks like this, R, and it has 3 indices, 0, 1, and 2. and initially they're all empty, but I can go along and say I want to set r of 0 to be the number 1, and that will do this. It will set r of 0 to be 1 right there, and have it hold information, and we can print it out now. It's saved. Okay? So that is what we want to do. That indexes into the array, we say, and sets its value. That's the term. Indexes into R and sets the value. Let's just say the array. And sets the value. Okay? So that works. That's what you need to do if you're just declaring an array and not specifying its stuff until later. You can also, just like other types, you can declare and initialize an array all at once. You can say, all right, type name, maybe int, array name, maybe r, give it a size, and then set it equal to, in curly braces, the stuff that you want inside of it, separated by commas. So this makes the array 1, 2, 3 immediately. Okay? That's what happens there. Okay, so if running this line, for example, will get me an array name, or actually let me just do it for ints. Let's do int r size 3 equals 1, 2, 3. This will make an array that looks like this in memory. Indices, it's got 3 of them, always starting at 0, and then they hold 1, 2, and 3. Okay? That's how that works. Okie dokie. So that is the first notation to declare and initialize an array, which is useful. Alternatively, because you're giving 3 things, C++ doesn't need you to specify the 3 here. Okay? You can just leave it out and it will fill in the 3 for you because you're giving those 3 things. Obviously, you want it to be size 3. So here's another option, like let's make an array of doubles. Double array 2, A2, square bracket, equals, I don't know, 3.14, comma 5.67. That will make A2, right? This will make A2 an array of 2 things, 2 doubles holding 3.14 in index 0 and in index 1 holding 5.67. Okay? So that's how you can do it. That's probably the most common syntax, because usually when you make an array, you got stuff that you want to put in it. Alternatively, if you're getting it from the user, you just have to declare it like this. Okay, so that is arrays in a nutshell in words and writing. Let me show you an example now. Okay, so here's my demo. Let's get 10 numbers from the user, and then we'll print them back out. Okay, we'll store them into an array. All right, so what I need to do is make room for 10 numbers. So the very first bit of my program better make room like this, like an array of 10 ints. Call it R or something. Okay, that's what I would like to do. So let's get them and print them back out. So int R size 10. So make an array called R of 10 ints, and then we'll fill R. Okay, what do we need to do? Well, 10 times for each index, R of 0, R of 1, ... we need to fill each of them. Okay, and so let's make a loop that iterates through all possible indices and fill that array. The last valid index is 9, so this is correct. So cout, enter the next element, cin into R of I, right? Because it'll start off reading into array 0, then array 1, then array 2, all the way to array 9. And then once we've got all the things, let's print them out. All right, with a space in between everything. So for int, do another loop, I is less than 10, I++. Now I'm going through the array and couting every individual element, R of I, with a space after, okay? And then we'll do like an endl after all of them. So here I am, making room, getting all the elements of the array, read into R of I, and then we're printing out every element of the array, okay? Cout R of I with a space after. So let's do that. So G++, arrays. Yay, so I don't know, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And so these are the things that I put inside of my array. And it saved them. It saved them right in there, and I was able to access them later. Isn't that cool? That's the first thing you can do with an array. Let's get the sum of everything in the array. And so what we're going to need to do there is something like this. Assume that the array holds 10 things, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Indices 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. And maybe I'm storing like 1, 2, -3, 4, 5, 6, 7. Now let's just do positive numbers right now. I'm going to change them to negatives so that when I talk about the minimum, it makes sense. Okay, so that's what I would like. So assuming I have an array like this, I can sum each element if I start a sum variable and bring each index of the array, each element at each index of the array into sum. So like add the 1 at index 0, add the 2 at index 1, make it 3, add the 3 at index 2, make it 6, right? Forever and ever and ever. All of these need to come into the sum variable, ... And I'll eventually get the right answer, yes? So that's how you can get the sum of all the things in an array. Int sum starts at 0, and then again, you're going to go through the array and add r of I, the current index that you're looking at, into sum, okay? Just like that. And at the end, once you've gone through every element, you visited every possible valid index, sum has been increased by that amount, you've got the right answer, right? Yay. Sum. Yay. So let's rerun. Let's make it 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And the sum is 55. Remember that from before. Okay? So, yeah, I hope that makes sense. It's just you're going through each individual element of that array and saving it somewhere. Okay? That's what we want to do. And then the last thing that we can do is try and find the minimum of all the elements of an array. All right? And this is probably the most complicated example of what needs to happen here. Okay? Minimum finding for an array. Let's pretend that our array is now 1 to -3, 4, 5, 6, 7, 8, 9, I don't know, -10. So here is the algorithm to find the minimum, okay? So first notice that if you're looking for the minimum element of an array, like apparently it's -10 here, but you don't know where it is, right? You must check every possible index. I'll abbreviate index to IDX, because the min could be anywhere. Anywhere. Okay, that's the first thing. And the second thing I want to say is the algorithm. The trick is to make a guess and keep on updating your guess. So what you do is guess. You might be right, you might be wrong. For the original array, you would have been right. Guess that the 0th index is the min. So pretend, guess, make a guess that the 0th index, whatever element there, is the minimum, and then go through the rest of the array and update your guess as necessary if you ever find something smaller, right? So initially, let me draw this in green so that we have something different to look at. Initially, we think that the min is 1, because we'll put array of 0 into the min variable. And then as we visit more things, we look at 2, okay, that's not smaller. We look at 3, oh, that's smaller. Let's replace my guess for what the minimum is with -3. Does that make sense? And then we'll visit more things. 4 is not smaller, 5, 6 is not smaller. Eventually, we'll get to -10. Oh, that's even smaller than my current guess for min, -10. And at the very end, after you've updated all your guesses, you visited every element, updating your guess as necessary. So after you visited all the elements, you have the true minimum inside of your min variable. Okay, and that's the algorithm. So let's go and implement that now. All right, so to the code with us. Let us look here and see what we need to change. Okay, so minimum is definitely the hardest algorithm here. So let's talk about that in depth. So we're going to need to save the minimum somewhere, so we better at least make a variable to hold the minimum. Okay, that's at least something we know we need. So let's do that first. Okay, sum all the elements, and then this is find the minimum element. Okay, so first, int min, we make a guess and pretend that the minimum is the 0th element. It's the first element in the array, right? Guess, or initially, make a guess that the 0th element is the real minimum. We will update that guess if we ever find something smaller. And since we're always going to update the minimum, our guess for the minimum, every time we see something smaller, we're always going to end up with the right answer every time we visited all the elements. Does that make sense? I hope it does. Please yell at me if it does not. So what we need to do now is visit every element, right? So for int I equals 0, I is less than 10, because that's how many elements are in our array, I++. Here's what I'll do. What we need to do now is, well, technically we don't have to start at index 0 because we've already put that into our minimum. Okay, so we can start at index 1. Every other index we need to go through now. Okay, so now we look through every other index in R, so 1 onward, and we see if we have found something smaller. And we compare the value at that index to our current guess for min. There. So here's what we'll do. So the value that we see is R of I, right? And we want to compare that with our current guess for min, right? Because if this is ever true, if the thing that we're looking at right now is itself smaller than what we think the minimum is, then we were wrong thinking that thing was the minimum, right? So maybe that's right here where we thought the min was 1, but we just saw -3. Well, a better guess for the minimum then is -3. Yes? That's the trick. So if we ever find something smaller, we better pretend that that's the min. That's a better guess, okay? Right. That's a better guess. So if we ever find something smaller, then make that our min, our guess for min. So min is equal to R of I now. Yes? So this is like, we just saw the -3, and our min was 1. Let's update min to be -3 instead. Okay? Does that make sense? That's the trick. It's possible that the array goes from 1 to 10, all positive numbers, and so the first element really was the minimum, but we're not sure. We gotta try every index, right? So that's that. And then, because we did this, because we've updated the min if we ever saw something smaller than our current guess, once we've had a chance looking at everybody and potentially updating our guess with everybody, then we have the true minimum, okay? Once we've seen everyone and gave it a chance to fight our guess of the minimum, then our guess is correct at the end, okay? All right, the true minimum value of the smallest element of the array. All right, so cout min. All right, so let's watch this working. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If it was the first one, the min's still 1, right? Starts at R of 0, goes through all the elements, We never found something smaller, so we never needed to update our guess. But maybe 1, 2, -3, right? 4, 5, 6, 7, 8, 9, 10. Now the min's -3 because we started with our guess of 1, but we found something smaller, updating our min as necessary. Everything else was bigger. Okay, so now our min is -3. And then finally, if I do my example that I wrote on the slides, 1, 2, -3, 4, 5, 6, 7, 8, 9, -10. We're going to update our guess for the min twice, right? So once we see -3, then we're going to guess that the min is -3. But then we come along and later see -10. Ooh, that's even smaller. That's a better guess. Yes? I hope you see how this algorithm is going to find the true minimum of the array. Okay? So get used to saying R of I a lot of times, because that's how you iterate through an array and visit each index. Okay? Usually with a for loop. So please yell at me if that wasn't making sense. That was the hardest algorithm for the day. Okay? So with that, I want you to try something. Okay? Pretend we have this array. We declare it int blah of 6, size 6, and then we go and we try and access index 7 of the blah array. Interesting. So what do you think is going to happen if I run these 2 lines of code? I try to access index 7, once to set it and once to get the value out and print it. Okay? So see if you can figure out what's going to happen there. And assuming you're back and you have a good guess, let's talk about it. So here's the array, right? The array is called, it's called blah, right? Blah. And it has 6 indices, which range from 0, 1, 2, 3, 4, 5, 6, right? 0, 1, 2, 3, 4, and no, sorry, just to 5. Got too happy there. So that's the valid indices of the blah array, and then we're trying to access index 7, which is way over here. Like 6 doesn't exist, neither does 7, but we're trying to access the all the way to 7, right? Those phantom indices. So what in the world is going on there? This is weird. This is part of blah. This is just other memory that your C++ program can try and access if you ask it to. This is memory that doesn't belong to you. Does not belong to you. So with that in mind, what do you think is going to happen here? You think it'll give you a runtime error, like, oh, you're trying to do something silly. Sorry, not going to let you have that. Not going to let you access that. Let's see. What do I want to call this? Past the end. .cpp. We're trying to access past the end of that array. Let's see here. So int blah of size 6. All that stuff. Okay. Dun, 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 dot slash past the end. Ooh, that's nice. It honestly depends on the computer, but it prints 42. Yay. Isn't that nice? That's fun. Okay, so it's going to print 42, and it looks like it also gave me a runtime error, but sometimes it won't even, okay? Like last semester I didn't get this error. It just print 42 by itself. Crazy. Sometimes it works, sometimes it doesn't. So the answer really is something else, because it did print the 42, and sometimes it's not going to throw a runtime error. Sometimes it just lets you have that memory and set it to 42, okay? So that is the idea. Actually, if I do this, I think it'll let me have it. Let's do int a, b, c, d. Let's make a few extra variables for reasons. Oh man, what about, let's do some more int r of size 100 down here. Come on. Yeah, there we go. See how now it lets me have 42 and it doesn't even throw a runtime error? So isn't that fun? Well, let's talk about that. The answer really is something else, because it might print 42, might have a runtime error. What we just ran into is the same thing that we run into when we declare a variable but never initialize it and then try to use it. It's called undefined behavior. Okay, it is undefined what happens in this situation because something so weird happened. All right, so technically you can try and access /set a weird index, an index to an array that doesn't exist. Like when the array is size 5, you get up to index 4. You can go past that if you would like, but you shouldn't really ever do that, right? You should never, ever, ever do that because that's undefined behavior. That's not your memory. It's somebody else's, okay? So it might work, usually will work if you have enough extra variables declared. Probably won't one day though, okay? On a different computer it might break everything. So the second you do something silly like this, you invoke the wrath of this thing in C++ called undefined behavior, which just means that you broke the rules of C++, and the compiler, if it is smart enough to notice you breaking these rules, it's allowed to do anything to your code because you're outside of the C++ standard at that point. So technically, the definition in the C++ language standard allows undefined behavior to like delete all the cat pictures on your hard drive. Okay, that is totally a valid thing that undefined behavior could do, but usually it just fails a little bit more gracefully than that. Okay, but I want you to know about the term because I'll use that again in the future. But that is something very horrible that we don't like. Okay, so don't ever try and access memory that isn't yours. That is called undefined behavior, and anything goes at that point. Maybe you'll get a runtime error, maybe you won't, maybe your program on your computer will work fine, but if you give that same program to somebody else on their computer, it will crash. Okay? So that is a problem, and now you know about it. Okay? So that's where I want to stop today. We'll come back, do more array stuff, and now you are ready to do your next lab. So after this lecture, go and watch the lab video so you can get started on that, okay? Because it's about loops, and those will be on the midterm, so you should get started on it as soon as possible, okay? So I'll see you in the lab video, and then back for the next arrays lecture.